Hi class, in this lecture here I want to continue in section 2.2, and what I want to do is I want to talk about a strategy for sketching graphs. So basically what I'm going to do here is I'm going to do an example where I walk you through every single type of concept that we've talked about in section 2.1 and 2.2, and then use all the concepts: increasing, decreasing, relative max, relative mins, to take a function and sketch the graph of it. All right, so what we're going to do is I'm going to walk you through all the steps here first, and then I'm just going to jump right into the example. Okay, so the first thing you want to do is derivatives and domain. All right, so in the first two sections of this chapter, we've looked at the first derivative and the second derivative. We're also going to note the domain of the function. We're going to find the critical values. So first, second derivative, domain, critical values. That's critical values are you're going to look where the first derivative either is equal to 0 or does not exist. Then we're going to look and find increasing, decreasing, and relative extrema. So what I'm going to do is I'm going to set this up using that table I did before, and then define the intervals increasing, decreasing. Then I'll look at that. You can figure out if you have a relative max or min, or you can use this second derivative test that we talked about in a previous lecture. Then from there, we're going to do inflection points. That's where the second derivative is equal to 0 or the second derivative does not exist. So that's where the graph is, changing from turning upward to downward or turning downward to upward. And then we're going to look at intervals of concavity, where things are concave upward, concave downward. And then we're going to sketch the graph. We're going to sketch the graph using all this information. And you're going to calculate plotting extra points as needed. And one of the things that you should note to do is you should find the intercepts when possible. Okay, like if you can find the x and y intercepts, that really helps plot the graph and make it look nice and neat. And sometimes you can't. Sometimes you can't do that. Okay, so here's the problem. Okay, we're going to just do a real nice simple polynomial function. Okay, so for this function, f of x is equal to x cubed minus 3x plus 2. Here's what I want to do. Find the first and second derivatives. Find critical values or critical values of the function f of x. Let's find the intervals it's increasing or decreasing, relative extrema, inflection points, intervals the function is concave upward and concave downward, and then we're going to throw it all together, and we're going to sketch the graph of this function. So what I encourage you to do while you're watching this lecture, you have the lecture and my notes printed out in front of you. But what you might want to do is, like, as I get to do the first and second derivative, find it yourself, pause the video, see what the answer is, and unpause the video and see what I got. And as we do for every step, that'll just help make this, a little bit more of an interactive learning process for you, and you'll get more out of the lecture. Okay, first and second derivatives. So let's just rewrite the function. So f of x is equal to x cubed minus 3x plus 2, I believe. Yep, minus 3x plus 2. All right, so f prime of x. Well, if you take the derivative of this, right? Bring the 3 down, 3x squared. The derivative of 3x is minus 3. That's great. And so the second derivative is just the derivative of the first. So bring this 2 down. 2 times 3 gets me 6x, and that's, the derivative of minus 3 is 0. So these are some really, really straightforward first and second derivatives. Okay? All right, so we got this. Next, it says critical values of the function f of x. Okay, so this occurs when first derivative is equal to 0. Okay. If you look here, the first derivative cannot, it's always, the domain is all real numbers. And it's the same actually here. I should have done this when we first started, but the domain here is negative infinity to infinity, obviously. So the domain is also all real numbers. So you just got to look where the first derivative is equal to 0. So you're just going to take the first derivative, set it equal to 0, and solve. So you're going to add 3 to each side. So you get 3x squared is equal to 3. Divide by 3. You get x squared is equal to 1. And when you solve by taking the square root, right, just remember you get two solutions. You get x is equal to -1, right, and x is equal to 1. All right, so we're on our way. We're on our way. Okay, we got the first, second derivative. We found critical values. So we're going to use these critical values, right, to help us find intervals the function is increasing and decreasing. So we're going to use our critical values, -1 and 1, to break up the number line, right, for the intervals we have. So we're going to go from -infinity to our first critical value. We're going to go from -1 to 1, right, our second, that in-between interval. And then we're going to go from 1 to infinity. Next thing you're going to do is you're going to pick test values. So just pick, I'm going to pick -2, I'm going to pick 0, I'm going to pick 2. And then remember you're looking at the sign of f prime of x here. So this was our first derivative, right? So just recall here. Our first derivative going back was 3x squared minus 3. So if you plug in -2, right, into this, -2 squared becomes 4, times 3 is 12, minus 3 is 9. So that's greater than 0. So what that means is the function is increasing on this interval, -infinity to -1. If you take 0 and plug it in, right, 0 squared is 0, wipes this out, and you get -3. So look at that, that's less than 0. So that means the function is decreasing on this interval from -1 to 1. And then finally, let's take 2 and plug it in. Well, 2 squared is 4, times 3 is 12, minus 3 is 9, so this is greater than 0. So we see now the function is increasing on this interval. All right, so we got the intervals that it's increasing and decreasing. So that's going to help us when we go to graph, you'll see. Okay. So we're moving along. Okay, so let's now find relative extrema, right? And so what I'm actually going to do is I'm actually going to use the second derivative test. Okay. So relative extrema, remember they occur at critical values. So what were our critical values, right? So let's look back. Our critical values were -1 and 1. So this was our function, right? F of x is equal to x cubed minus 3x plus 2. And so here's what we're going to do. We're gonna take these values and plug it into the second derivative. So our second derivative here was just 6x. Very, very, very easy. So what's the sign of -1 when you plug this in? Okay. So that's less than 0. So what does our second derivative test us? Well, it works the opposite way you would think, right? So going back, if the sign is less than 0 here, you have a relative maximum. So relative max at this point. -1 comma f of -1. All right, well, if you plug -1 into this, right, just over here, f of -1, you get -1 cubed minus 3 times -1 plus 2. Well, that gets me -1. This becomes +3 plus 2. So that gets me 4. Okay, so we have a relative max at this -1, 4. So what that means, we sketch the graph. It's going to go increasing, hit this relative max, and then decrease. Now let's take the other side here and plug in the other critical value. So this is greater than 0 here. So what that means, when the sign of the second derivative is positive, evaluated the critical value, we have a relative min. So if you plug 1 in here, right? So you're going to get 1 cubed minus 3 times 1 plus 2. So you get 1 minus 3 plus 2. You get 0. So you know what we found? We found an x-intercept. That's great. So it turns out we have, that's amazing. We found one of the intercepts. One of the intercepts turned out to actually be a relative min. All right. So now let's find inflection points. And then from there, intervals is concave upward and downward. And then let's sketch the graph. So inflection points, they occur where f double prime of x is equal to 0 or f double prime of x does not exist. Well, in our problem, right, f double prime of x here was 6x. Well, where does that equal 0? That's awesome. It just occurs when x is equal to 0. That's the only place that can happen. Just divide both sides by 6. So what that means is we have an inflection point at this point, 0 comma f of 0, which is awesome because this is the y-intercept. So if you plug 0 into our original function, right, that goes away, you just get 2. Okay, so I'm just gonna note that over here that that's also the y-intercept. Look at this, getting more done. All right, so the next thing we do before we sketch the graph, we're going to do intervals. The function is concave upward or downward. So what you're going to do, where you have this inflection point, or where it occurs at x is equal to 0, you're going to use that to break up the interval for the number line again. So interval concave up or concave down. So you're going to set up that table, right? So the interval. So you use this value where the second derivative is equal to 0 to carve up the number line. So you're going to go from -infinity to 0, and then the next interval is going to pick right up, 0 to infinity. Again, you're going to pick a test value. So here I'm just going to pick -1, and it's between 0 and infinity. I'm going to pick 1. So our second derivative was 6x. All right, so again, you're just going to look at the sign. Of the second derivative at this test value. Well, if you plug -1 into this, you get -6. That's less than 0. So what that means is you're concave down on this interval. And if you plug 1 into the function, you get 6 times 1 is 1. That's greater than 0. So you get concave up on this interval. All right, so look, going back, we've done a lot of work on this. You can tell these problems take a while. Okay. All right, so what you're going to do now, this is the hard part. Okay, you're going to sketch the graph. So here's what I do first. Okay, I'm going to plot the points that we have found. I have a relative max at negative 1, 4, and a relative min at 1, 0. We also had a point of inflection at this 0, 2. So let me plot those first, right? So here's negative 1, 4, 0, 2, and 1, 0. So now, you know what happens here? It helps to maybe plot a few extra points. And I'm just going to do, this, 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 and this. So what I'm going to add to these 3 points is I'm going to add this one. So negative 1, what happens at negative 2? Awesome, I found another intercept. And then what happens a little after 1? You go 2 to 4. So look, going back, now you're going to use your intervals of increasing, decreasing to help you. Okay, so it's increasing from negative infinity to negative 1. So what that means is like go to the right, the graph is going to go up. So look, the graph is going to be increasing. And my graph is going to be pretty not great here, but hopefully you kind of get the idea. Until it hits this max. And then it was decreasing from negative 1, look. Decreasing from negative 1 to 1. And then this was a relative min. It's going to hit this. And then it was increasing from 1 to infinity. And I really apologize. My graph isn't great here. But, sketching this with the stylus isn't the easiest thing. And that's how you do this, right? You plot your points, maybe get a few extra ones, and then use those intervals of increasing or decreasing to really, really sketch this, this graph. All right, class, I know this was a lot in this example here, but you'll get a chance to practice this in your homework. And as always, if you have any questions, I am here to help.